Hello everyone, welcome back. Today's video is on resources, reserves, and ores. The learning outcomes of today's video is we're going to define all the parts of a natural earth resource. We're going to define what ores are. We're going to evaluate what minerals make useful ores. And then finally, it will evaluate the supply and demand of different earth resources. Here we have a lithium brine pool, which is a really popular way of extracting lithium from really saturated brine solutions deep in the earth. So resources and reserves, resources are a material that has some inherent value to an individual or society. There can be water resources, food resources, and in this instance, we're talking about earth resources. So materials that come from the earth, minerals and rocks that have some chemical in them that present some value to civilization. Reserves are the quantity of that resource that can be recovered with existing technology in today. And so here in our figure, we have reserves represent material that we know exists, that we have proof exists, and then that is presently economically viable to extract. So that is the lithium that's being mined currently represents our lithium reserve. Cumulative reserves represent the current reserve that we're working with, and then material that's also already been consumed, which isn't represented on our figure here. And so if I'm talking about cumulative reserves, we're looking at what we're currently using and have access to, and then what we have used in the past already that's been taken care of, accounted for. Sub-economic resources are reserves, or not reserves, but resources that have been found. We know they exist, but we can't extract them for whatever reason. Whether the technology to extract them doesn't exist, it's not possible with our current understanding of earth scientists and sciences and chemistry, or there's no, the cost of extracting it is too high. The technology exists, but we can't, and we don't want to do it because it just feasible, it doesn't make sense economically. So that represents our sub-economic resources. It's identified, we know it's there, we have proof that it's there, but it's not presently economically viable to extract that resource. Then we have our hypothetical resources. Our undiscovered resources is composed of a hypothetical resource and a speculative resource. And so a hypothetical resource is that resource that is to be found in known areas. So it is resources that we can speculate exist based off of our understanding of sedimentary rock banding or different sort of indirect measurements. We don't have a direct proof that that resource exists, but we have some good idea that it's there in areas that we're currently working on and currently mining with in the present day. Speculative resources are resources that are to be found in unknown areas. So it's really hard to know what you don't know, and that's basically what a speculative resource is. We're speculating that it might probably be in an area that we don't know currently. So expanding our current understanding and leaving some room for sort of scientific discovery, because there is advancement still happening in the mining space and resource recovery. And then that whole thing creates our estimated total resource. How much that we could ever possibly have access to is all of these things added together. And so here we have some global resources. We have chromium, cobalt, copper is really important in semiconductors and phones. Iron is extremely important in building buildings, manufacturing steel, lead, manganese, nickel, all very valuable. These reserves are extremely large. I think these are in like millions of tons potentially. I cut off the units there, but you'll see that the projected lifetime of these reserves, so we have our production, the amount that we're extracting from the earth, and then if you divide that by the reserve that we have or estimated resource potential, you get a projected lifetime that isn't extremely large. So some of these are within our lifetime potentially. Lead 18 years of a projected lifetime of those reserves that we have. Um, and so hopefully technology changes and we'll be able to access more of that. But currently, if things just are staying on the same course, we only will have 20 years left of our access to lead, which is kind of surprising. All of these are quite low numbers, which is also surprising. And so an ore, bauxite is an aluminum ore. This is where we get aluminum from. And an ore is a rock that contains a high concentration of a useful metal that we want. Um, so there's sort of ambient concentrations of a lot of different earth elements and everything, but ores are rocks where we're finding like really high concentrations of that material, and that's what makes it economically viable to work with that rock instead of just working with sediment that we're pulling out of the riverbed or something like that, because there are lots of elements in that too. There's aluminum in the feldspar in a riverbed, but we're mainly looking for aluminum in this aluminum ore because its concentration is that much higher than feldspar, which is so readily naturally occurring. Ores are usually a mineral oxide or a sulfide. Most of the minerals that you think of, aluminum, copper can be present as a copper oxide or metallic copper, but mainly it is as an oxide. We live in an oxidative environment. When these elements are exposed to air, they react with air and they create a metal oxide, or if they are exposed to sulfur within the earth, they'll make sulfides. So lead comes from a lead sulfide mineral. Iron can come from an iron sulfide mineral. It mainly comes from an iron oxide mineral. And so these are the types of minerals that we mainly use for ores because they have extremely high concentrations of that metal in them. It's usually just the metal and oxygen or the metal and the sulfur atom in that molecule. Most metals, like I said, are rarely, if ever, found in their metallic state. You will never find iron naturally occurring in the environment as a hunk of metal iron. It's going to be involved in some iron ore, some rock, because it is so reactive that over the geologic time scale, it just is not something that we're going to encounter. And so you may think, we're running out of time. Those time scales were 40 years for some of them. But as resources grow thin, the price of those resources is going to become more expensive. And that's just natural supply and demand. As our supply goes down here, your price goes up. Your price is going to go up. And so this leads to innovation and revisiting technology that was potentially deemed too pricey in the past. Also, other technological advancements may allow you to revisit mining that and chemical reactions that were previously to energy effective. And so we're looking at a time scale here where we're going to make so much renewable energy that renewable energy is going to be so cheap in the near future. It's already cheaper than natural gas in some places. And so in this scenario, we have an excess of electricity. And so some of these places were able to channel this excess electricity into a ore extraction process that allows us to turn our rock into a valuable metal using this excess renewable energy. And so that's an innovation outside of the mining space that's impacting the mining space and allowing for technological advancement, and then being able to access those sub-economic reserves that were previously too costly to access. Fracking is a fantastic example of this. Gas used to be, very pricey in the, I think the late 2000s. And so with advancements in fracking technology to be able to use existing wells, if you're not familiar, fracking is basically injecting high pressure liquid into these fracking wells that fractures the rock and then keeps that rock open with some grit or sand or something like that. And then it allows for you to extract oil and gas from areas that were previously not being accessed by your manually drilled pump or drilled hole. And so it allowed for an increased access of resources and allowed you to tap into that sub-economic reserve and drop the price of gasoline as a result, because the supply was a lot more, because the United States was also able to supply a lot more gasoline for Americans, which caused the price of gas in the United States to go down. And so that concludes this video about resources, reserves, and ores. Feel free to reach out to me if you have any questions, and take care.